Hello folks, this is Tom from anti-proton.com, and today we're going to discuss isotope identification. I've been doing a series where I've been showing you various isotopes and their spectrums, and that's nice when you have a sample from like a company or something like that. But what happens when you have a sample like this? I don't advocate home food testing, of course, because of the fact that it's very, very complicated and it's a human health issue. But somebody actually sent me this, a friend of mine actually sent me this. No, I don't take samples normally, but I did get this one from somebody. And so I figured I would use it as a good example. This sample is a little bit elevated on beta radiation, just a little bit, which I think I know what the cause is, but we're going to find out right here today what the cause is of that. And I have another sample right here. This is a mineral sample I have. And the curious question is how to determine kind of cold, what is something? What methods can we use? Now, when I take a scintillator and put it near this sample, I don't get much of anything from it. The sample is not very hot. This the gamma scintillator here shows almost nothing from it whatsoever. The other sample, the mineral sample that I have, is a little different. It goes hard over. We have a background of 2,000 counts per minute, but this sample itself is almost 100,000 counts per minute. So obviously this one's a hot one. So we're going to look at both. The idea being that we can get a feel for a nice hot sample and a not so hot sample. To do this, we're going to be using the Spectrum Techniques Universal Computer Spectrometer. That's the UCS-30. We're going to be using a 1.5 inch, that's a 38.1 millimeter, sodium iodide thallium doped scintillation counter, which is plugged up. It all goes into this unit right here, and a laptop connected to it. I have a lead castle, which I've created from lead bricks. I'll put it in links where I got all this stuff. Lead is needed when you're testing something that's very low in activity like this. By the way, I know these look like noodles, and you're probably thinking Fukushima, Fukushima, Fukushima. These noodles were much older than Fukushima when they were packaged. So if they have any contamination, it wouldn't be from Fukushima because they predate Fukushima. Just for the record, so nobody gets the wrong idea. I'm going to go over how I do this and what I find. So to start with, let's get the detector turned on and get it calibrated because that's very, very important. Step 1, power on the detector. It's now powered on. Step 2, I'm going to show you a little bit about how the testing chamber works and what's inside of it. Now these bricks of lead have been painted in a clear coat and a kind of a golden colored paint to prevent the lead from being contaminating and getting all over the place. But they've chipped a little bit, and it's just a smart idea for $2 or $3 to buy and use some of these little gloves when dealing with lead. Because quite frankly, this lead can affect you just as badly as radiation can, for lower level radioactivity. Let's move the samples away because we don't want to contaminate our spectrum. And let me open up the lead testing chamber and show you what's inside. Alright, so here's the lead testing chamber. I'm pulling the lead off, and I have to be careful. This stuff is so heavy. They're like 5 or 6 pounds of brick, something like that. They can easily cause the table to collapse if you're not careful. So be careful when you're doing this. Inside of the lead testing chamber, let me kind of move the camera a little closer so that you can see. There's a small area that I've created for the bag to go. This is a plastic bag right here that will be full of the noodles, and they'll go in here. If you have a little more money, time, and area, it would be nice to make a larger testing castle that's much bigger. I actually have more lead than this, but the table couldn't support it, so this is all I get to work with. So you can spread this away. If you get that lead a little bit away from the detector crystal, that's actually a better idea than having it right up against it. It's also a good idea to put multiple types of metal in here, like sheets of copper, for example, are very useful, sheets of tin. Now inside of here, we have the detector. You can see here's the detector right here. This the crystals in the front with a photomultiplier tube in the back. And this will detect the gamma rays that hit it, and the photomultiplier tube will amplify them and send them out as little pulses of current. So let's stick that back in. This, by the way, is roll up lead sheeting. Now, This is a beta shield. It's just a piece of aluminum, and I stick it in between the detector and what I'm detecting, and it will block some of the beta radiation hitting it, which is better for the sample. You really don't honestly want the beta radiation to strike the crystal detector if you can, because it makes the sample not look as good. Anyway, so let's get that in place. I want to stay up today. Now let's take a sample source disk. This is Cesium-137. And we're going to take this, and this is what we're going to put in here and test. And this is what's going to allow us to calibrate the machine. And I'm going to kind of like lie that down in there so it's pointed at the detector. So there it is, pointing at the detector. Now let's fire up the detector and let's get ourselves a good calibration. So I'll cut the camera off now and switch to the computer. Alright, so we're on the computer. We're going to start the USX software. There it goes. Loading hex file. There it goes. Okay, so now we're in the software. This comes from the detector. Voltage is set to 650, which is pretty much where I usually use it for my detector. We're going to cut it on. High voltage is on. Let's clear the regions of interest from last time we used it. And now let's start accumulation. Let me change the where is it? Pixel size, so you can maybe see it a little better. There we go. Now this is a pretty straightforward Cesium-137 spectrum that's forming right now. All right, let me put the source a little closer to the detector. There we go. Now you can see it forming. All right, move the source back away again. So basically we could calibrate ourselves pretty easily. In fact, let's see if we're already actually pretty well calibrated right here. I've calibrated with this point right here and this point. And I'm going to calibrate it again in a second to show you how to do it. So I have a pretty good belief that what's in those noodles that's causing them to be radioactive is probably potassium-40, and the reason for that is because potassium, uranium, and thorium are your three common naturally occurring radioactive materials, and there are three of the things you should look for first. It's not that you shouldn't look for anything else, but those are very common, and the gamma energy for potassium-40, well, let's look it up. Let me minimize this for a second. I have a list of energies right here, and I'll provide this list if you guys like. Let's look up potassium. Now at this point we're making a guess. This is what's called a supposition. We don't actually have any idea what's causing the stuff to be radioactive, but we're just guessing. For a potassium hypothesis, we would need to see a gamma energy at 1,461 kiloelectron volts. It's a pretty low branching rate, so it would be hard to pick it up. But that's where we would expect to see that energy. All right, and for all the other ones that we see here, most of them don't go over about 15 to 1600 keV. So let's go back and make sure that this thing is good to catch 15 to 1600 keV. Now where's 1500? It's somewhere right around here. So I should probably drop this back a little bit. We probably want to squeeze this up a little bit, make this peak shift a little bit more to the left. So what I'm going to do is drop that fine gain just a little bit. When the fine gain goes higher, the peak shoots out higher. Same with coarse gain. So we're going to drop that fine gain a little bit. Let's drop it down to 1. Let's clear the spectrum and let it build again. And now you see that this is shifted over just a little bit. It's now over almost 100 kiloelectron volts less. That should be good enough for what we're doing. So let's give this a moment. I'll put the source closer to the detector again. Let's give this a moment to build up, and we'll calibrate it. Now, if you're wondering what I just did, I made some guesses as to what I think was in the noodles. I didn't say what was in them. I don't know. I made a guess. And then based on that guess, I looked up in a lookup table what the highest energy was I could expect to find. Right here, 1461 keV. Then I looked back at my sample and I saw the highest energy that this sample is putting off this calibration source, which is 662 kiloelectron volts. So I figured if this is 662, double that would be what, like 1300? And it is 1300, which means that 1400 keV for the potassium, if that's what's in it, should fall right around here somewhere. So we just wanted to make sure we had that about right. Okay? Now, it's always best when testing for an isotope to calibrate with the isotope you're testing for, but you can't always do that. So we're going to do this without that. I have plenty of potassium 40, but I kind of want to show you how to do it without that, because you never know. Like, what if you were looking for plutonium, for example? It's not like you have any of that sitting around, so let's do it. Okay, so we have a pretty good spectrum. Let's stop this. Let's calibrate. All right, step one. We'll select this area here. Come on. All right, well, we'll just go the other way since it doesn't want to select. That's a region of interest. We know that this is probably 32 kiloelectron volts because we know what Cesium-137 looks like. Just kind of trust me on that one, I guess. And then we know that this is 662. It's actually 661.66, but we'll call it 662 kiloelectron volts. We know that, all right? All right, so before we can do a calibration, what we need to do is we need to get rid of the calibration that's there at the bottom. To do this, we'll go to Display, where is it? Settings, there we go. Settings, Uncalibrate. Now when we hold our mouse over here, we see the centroid is at 14, and we know that that means that that's the mathematical center of this whole peak, 14. And we know 14 is equal to 32 kiloelectron volts. So let's go to Energy, 2-point calibration, change channel to KeV, kiloelectron volts, thousands of electron volts, hit select, or set. Let's set 14 as the channel, and we're going to tell the computer that on this XY graph that channel 14 is equal to an energy of 32 kiloelectron volts. Select. Now let's go down here and look at the big boy. It has a centroid of 350. All right, so at channel 350, the mathematical center, we say that this is approximately equal to 662 kiloelectron volts. We hit select, and now the computer calculates. We believe now that this is calibrated roughly correct. From here to here, it's going to be pretty well calibrated. The change in energy with respect to channel is not linear, it's slightly curved. So right around here and right around here, it's going to be the best calibrated. Here, it's going to be a little bit less calibrated, and as it goes this direction, it's going to get less and less and less and less and less. That's why it'd be nice to have a higher energy source over here for calibration, but we're not going to do that today. We're going to do it nice and simple. Okay. Now, if everything is correct, we believe that potassium should fall somewhere around 1461, right? That's what that chart said. 1461. So somewhere right around here is where potassium should fall. Excuse me. Let's clear this out, run it again, see if everything holds up the way it should. All right. Now, the temperature in the room, the temperature of the device running, and everything are changing over time. Normally, I like to let everything run for almost an hour before I even try to do a test, because temperature changes make a big difference. We're not going to do that right now for simplicity's sake, but typically I would suggest doing that, because if you notice, the centroid of this now the centroid's not referring to channels, it's referring to kiloelectron volts, is a little bit less. That means the temperature is going up. That means the point at where the channel being read is actually going down. So it's kind of interesting little thing about crystals. Basically put, if the temperature in this room right now and the temperature of the instrument were to drop by, let's say, 10 or 15 degrees, this peak would actually show up over here. Whereas if it were to go up, if it were to get nice and warm in the room, if the machine were to heat up a lot, this peak might go down a little bit. Does that make sense? That's a characterization of how crystals work. It's a property of them, if you like. But anyway, this is pretty close, and we'll be plus or minus a little bit. So let's stop. I think we're good. And now let's prepare the sample, and we're going to do the test. All right, we're ready to test now. We're going to start with this little box which contains a rock, probably uranium, probably thorium, could be potassium. Between uranium, potassium, and thorium, the highest energies we're going to be looking at were from potassium. So this should be lower than that, so it should fit in nicely with what we've already calibrated. So let's get rid of the calibration source first. This needs to be moved far away from the sample area. And when I mean far, I mean like far. And put behind lead too, because it can interfere with the spectrum. I'm going to put this right here, but I'm going to move it away before we do the actual test, because if you just put it right beside the unit, this will pick up a Cesium-137 peak that you will think is in the sample, but it's not. So we're going to take this little sample and stick it in here, and we're going to put the top over it, and that should make for a good, clean spectrum. Alright, we're going to run this now, see what we get. Alright, we're going to take a spectrum now and see what we get. Let's clear our regions of interest from beforehand so they don't interfere with our test, and let's run, see what we get. Now this is a powerful sample. As you saw, it had over 100,000 counts per minute on the scintillator. So we can reasonably expect that this will be a clear sample. You'll find that really potent samples, ones that have high activity, tend to show up pretty quickly. They're easy to see. They don't take hours and hours of running to figure them out. We're going to run this sample here for 5 minutes, and then we're going to take a 5-minute background, and then we are going to see what we get. Actually, you know what? We may not take a 5-minute background, and the reason is because this sample is so pronounced that I don't think I need to take a background. I'll explain what taking a background means in just a moment. For right now, let's just worry about seeing what the sample looks like. So we'll come back in about 300 seconds to see what it looks like. Alright, so 467 seconds has gone by. 461 of those seconds, the detector was able to detect what was going on. So we lost about 6 seconds to dead time when the detector was unable to detect anything because it was being saturated. This was a pretty high activity sample, that would be why. Now, a lot of people would be thinking at this point that I would use an auto isotope detector, but I won't. Not only because this doesn't have one, but also because auto isotope detection is fraught with miscalculations, with misreads. When they do them in a laboratory environment, those units are temperature controlled with temperature stability algorithms built into them, and they can actually do that. For a unit like this, a crystal detector, temperature plays a humongous role in where things settle. I can already tell by looking that there's been a little bit of temperature change as this spectrum has been calculated. And so we're going to use the home radiation laboratory method. We're going to do what the person in the home rad lab, that's you and I, who's an amateur and an enthusiast, should do versus what you would do in a lab. In a lab, your system would figure it all out for you because it costs, $50,000. Ours does not. The two main methods that I like to use in the lab are, first, a comparative method. You compare the spectrum you see against other spectrum that you have taken, or other spectra, if you want to be correct, spectra that you've taken, to see if they match up. You basically compare them to see if they look about the same. The second method you can do is you can pick specific peaks and you can look them up in a lookup table. And that second method breaks into two methods itself. The first one is to look up common isotopes. That would be like that little chart I showed you a minute ago. And the other method would be, if that fails, to open up huge exhaustive lists of gamma energies and go down them looking for the right gamma energy. You rarely have to do that unless it gets really confusing. Something to know about crystal detectors like this is you will not always be able to figure out what every single peak is. Sometimes peaks are like this guy right here, because I actually know what this is, are actually generated from the isotopes. Sometimes other peaks are actually created as a result of interesting interactions inside of the crystal, which I can go into and explain and have been doing and will continue to do in some of my videos about other isotopes. So let's start out. Let's look at some pictures of other spectra and see if we can actually identify this one from it. All right, let's look at this guy. Yeah, this doesn't look like this. That's Americium-241. What about this one? Nope, doesn't match. That's Cobalt-60. What about that one? And that's Cesium-137. We saw that earlier when we were doing the calibration. Remember that common shape? This one's been all solved out too. All right, what about this one? This little bumpy thing here kind of reminds me of this a little bit, but it's not the same. That's depleted uranium. Potassium? Certainly not. What about this guy? Well, there's an interesting one. Look at this. 1, 2, 3, 4 peaks that are together, 4 peaks, and then there's a bump over here. I have 1, 2, 3, oops, I set a region of interest accidentally. Let's get rid of that. Clear region of interest. 1, 2, 3, 4, and then a bump over here. That's interesting. Let's switch this to a linear view and see what it looks like. Linear view. Yeah, that looks a lot like that, doesn't it? Let's check the others and see if there's anything else out there. There's thorium. Reminds me a little of thorium, but not enough. There's not those little bumps right there. And what's this? Here's another uranium. Look at that. Reminds you of the uranium, doesn't it? 4 bumps and a big bump. The bumps, by the way, are photo peaks. I shouldn't call them bumps. But yeah, I'm pretty sure that what we're looking at here looks like natural uranium, doesn't it? Let's see. Natural uranium. Let's go look it up in the lookup table and see if it matches. All right, for uranium hypotheses, here's some energies. And let's look at some of the ones that have asterisks, which I've commented off as being the stronger ones. There should be a peak at around 186.1 kiloelectron volts. 186.1. That's right on 186.1 right there. So we can probably say that this is reasonably likely to be radium-226. All right, what's the next peak we should see? We should see one at 241.98. That's 242. That's pretty much right on the dot. 241, 242. It's off by 1 kiloelectron volt, which isn't much. So 242, yeah, that's probably that. Next one, we should see 295.21. See if this one's that. 294, 295. Yeah, it's off by 1 kiloelectron volt again. That's still pretty close, isn't it? Right on the dot. All right, what about this guy? We should see that's really, really low. Here we go. 609 is another strong one. 609 kiloelectron volts from Bismuth 214. 609. Yeah, that's almost right on the dot for 609. See 605, 607, 609. Let's highlight this is probably Bismuth 214 right here. So what's this guy right here? 350, 352. Let's see if it's on the list. That needs to be accounted for, right? Yep. Oh, I missed that one. 351.92 is another strong one. 351.92, right on the dot almost. All right. Well, that takes care of that. This is obviously containing uranium. It could contain other things, though. Let's see. For example, what is this big monstrous thing? It's actually kind of a double peak stuck together. There's one main peak that's up here at around 78, 75, somewhere in there, kiloelectron volts, and there's another peak that looks like it's stuck in here around, around 95, 97. Let's see if those exist anywhere on here. 95, 97, that could be these two guys right here, these thorium peaks. Those could be thorium peaks. They do fit the right place for thorium-234. And we know that 75 to 80 is usually lead from our background shielding. So let's clear this particular ROI and set it a little differently. Let's say that that is the first ROI for lead. And let's say that this could be thorium-232. And what's this right here? There's a little jump right there, a little bounce around 148, 150. Anything around 148, 150? Yep. Uranium-235. Could be. These low energy ones like right here that are not picking up very much, these were not low energy, but low intensity ones, these are too low for us to be sure of on this chart. Let's switch back to logarithmic for a minute and see what we see. We have some more stuff going off over here, and if we were to look up the fact sheet on Bismuth 214, Bismuth 214 appears right here, excuse me as I cough. we discovered that some of these guys are actually from bismuth 214 as well. Interesting. Anything from potassium? And this right here could be potassium. Potassium should be right. No, it couldn't be. This potassium would be at 1461, and that would be right there. So no, that's not potassium at all. This is probably another one of the, probably bismuth or something like that, one of the higher energy ones. I typically work down here in the lower energies, and I don't usually look up a lot of these higher energy ones, but we could. I bet we would find them to be what we think. Like, for example, let's look up on a nice high one, like bismuth 214 at 768.36. 768.36. Let's see if we can find it. 768. Right there. In fact, look, 767, 768. There it goes, right in the dot. And as you see, there is a peak right there forming. Not very much of a peak, but if I expand it, you can see it is right there. So this is not a fully solved spectrum, but we can reasonably conclude, based on the actual data that we have a sample of uranium. And for the record, I can conclude that this is a sample of gumite that came from Ruggles Mine, New Hampshire. I already know what it was. It is uranium. And then we could all go down here and solve all the rest of these little peaks here if you wanted to, but that would take some time. And once we had identified all of these and gotten them completely listed, we could save these to our list of known spectra. All right, so let's clear this. Let's put in the noodles. And now what we're going to do is we're going to take a 1 hour test of the noodles, and we're going to take a 1 hour background. And then we're going to take the background spectrum and subtract it from the noodles, because there is a background in this room. There's radioactivity in this very room, throughout all of the house, throughout all of the state, throughout all of the country, throughout all of the world. There's radioactivity everywhere constantly. And so we want to kind of subtract that from what's in the noodles. That being the case, I'm going to start with the background, and then I'm going to take the noodles into account. So let me switch back to the other camera. All right, so let's take the lead off. Before we take the lead off, you might find this interesting. Let's cut on the scintillation counter and see how well the lead protects us from the uranium. Now let's put that on the ×10 scale so you can actually see it. Not much of anything. Even though we have a big chunk of uranium, we can't see it. We're only getting 2,000 counts a minute. Let's take that lead off and now see what we get off the scale. Apparently the lead does its job. Alright. So let's get this off. Get this out of here. And what we're going to do is we're going to put this testing sample back in it. The Cesium-137. I don't need the glove for the Cesium-137, so in case anybody complains. For some reason, every time I put a glove on when I hold one of these things, I get like a whole bunch of negative comments. I don't really know why, because it doesn't really matter if I'm wearing the glove. This is fully sealed, but I don't know why anybody would care, but I always do. I always get like a lot of comments. Alright, so anyway, let me put this sample back in here. And we're going to put this away. Oops, hit my computer. And we're going to recalibrate quickly just to make sure that our calibration is still good. And then as soon as we're done calibrating, what I'm going to do is close this back up again, and we're going to take a background for 1 hour. Alright, so let's take a background now, because the unit's been on for a little while and we want to make sure it's still calibrated correctly, because calibration is very important. Look at all those little regions of interest I put in there are still there. I need to remember to clean those out more often. So I'm holding the source up near the detector to get it to run a little faster. But, oops, sliding all over the place. Alright, so there we go. We have a pretty good sample at this point. Stop it. Clear the goofy ROIs that I don't need. Select the regions of interest. Now, I actually don't know what's in the sample of noodles. I really don't. Meaning it's possible I may not be able to figure out what it is. So you get to watch me fail if I can't do it. Isn't that cool? I'm not kidding you. I actually don't know what's in this set of noodles. I tried to detect it with my Polymaster, and I got back kind of like null results, nothing really actually good. So I'm going to try it now with this more powerful detector. So you could actually watch me fail, which isn't really too hard, because if you watch my videos, you see I have like little errors all over the place. Actually, failing is pretty normal for me. All right, so the calibration is a little off. I think it's a little off. See, it shows the centroid as being 561 when it should be 662. Or sorry, there you go. I failed right there. It shows 651 keV as opposed to 662. So it's off by like 10 or 15 kiloelectron volts. So we're going to go to Settings, Energy Calibration, Uncalibrate, and we're going to recalibrate this thing. Not because it needs a tremendous amount of change, but a little calibration won't hurt it any. It's always a good idea to recalibrate, recalibrate, recalibrate. But remember, do not recalibrate between doing a background and doing a sample. That's not a good idea. You need them to equal out. So we know that channel 14, that was the centroid, the mathematical center, it's not actually the mathematical center, but it's close enough. So if you have a pure mathematics degree, don't yell and whine at me about that. If you know it's close enough. That should be 32 kiloelectron volts. And now for this next guy right here, 344, let me hold the mouse over it again so you can see that. See how it says centroid 344? That is the approximate center of that. We know that that should be 662 keV. It's about where it was before. It's changed a little, but not much. So stop, clear, go again. Hold the mouse over it and see what we get. That's holding pretty steady. All right. Now let's stop this. Let's clear this. Let me put away my source. So put away the source, put away the detector. All right, put these far away from one another. And where's that little sample? Uranium sample. Put that far away over here too. Okay, so none of these are anywhere near the detector. Now you can't see this because I'm just talking. I'll show you in just a second. Covering up the detector so that nothing gets into it and it's all nice and secure and ready to go. Now I'm going to set this now for 1 hour. So let's do that right now. Let me take off my glove and set this for 3,600 seconds. So actually, let's make sure. Let's go to time. Live time is how long the detector's been detecting as opposed to real time, because high count rates can change that a little. 3,600 seconds. 3,600 seconds is 1 hour, just in case anyone isn't aware of that. So set, clear all regions of interest, and I'm going to set this thing to go. There it goes. And I'm going to set it to linear view. And what we're going to do is we're going to leave, and I'm going to leave this on time lapse, so it's like the time sped up, you know, so you see the time speeding up. And I'll see you back in 1 hour. All right. Let's double check that we're still recording. Yep. Okay, so we've ended 1 hour of a test, and as you can see right here, this looks like an interesting little background. This right here is from the lead shielding. You can see the lead shielding right there. If we switch to a logarithmic view, you can actually see the 3 fingers of uranium. Remember the numbers where they were beforehand? You can see bismuth 214, you can see lead 214. These things are what we identified with the uranium sample, which is why I did it first. I wanted you to see. There's a little bump right here, right around 495, 500. This is actually most likely from higher energy particles hitting the detector and causing antiprotons. Then there's some other buildups, mostly from bismuth. I think that it's, let's see, where is it? I think that it's reasonably likely that this is actually potassium, which troubles me because that means my calibration can be off a little bit. So what we're going to do is we're going to quickly save this and then run a test to see if that's true, and then we're going to test the actual sample. This will make sure our calibration is good. I told you not to change your calibration when you're doing a background, but sometimes you just have to recalibrate. There's nothing you can do about it. So let me save this, and then we'll move right along. All right, so we're going to go to Isotope ID, noodle, I think I spelled that wrong, background, 3600 seconds, save. All right, so that's the background, and it's saved. Now, let me remove the lead quickly. You can't see this because, of course, I'm doing this external to you. And I'm going to put in a can of potassium chloride light salt. And I'll turn the video over so you can see it after I get this going. But I want you to first see what the spectrum looks like with some pure potassium chloride. Actually, it's not pure. It's actually potassium chloride and sodium chloride mixed together. I think this is actually a potassium. So now that we've taken the spectrum, let's close this quickly and quickly just run a sample and see what we get. Switch to linear. And let's give this about 10 or 15 minutes to see if potassium shows up where we expect it will be, and then I'll be right back. So I just want to double check that this is right. All right, after about 10 minutes, we can see for sure now that that's where potassium 40 is. So we're going to recalibrate again, and we're going to recalibrate and make sure we get this right. Our background doesn't have to change because we already know the background is pretty much right. We just don't have our energies mapped to it correctly. It's not that the data is wrong or anything like that. So here's our potassium 40. And let's see here. Let's grab the Cesium-137 again. Remember, you spend so much of your time calibrating and not as much of your time testing. All right, let's put the Cesium-137 into place and start accumulating again. And there goes the Cesium-137 really quickly. Let's stop that. So now we know where that is. Let's make sure it's still calibrated correctly. Oh yeah, that's calibrated right on the dot. And the and the X-rays looks like they're calibrated too. So settings, energy, calibration, uncalibrate. Let's do a 3-point calibration. Just like I showed you. First thing we do is look at this guy. The center is 14. So channel 14, we noticed happens to be 32 kiloelectron volts. Number 2, the centroid is 344. We know that channel 344 is about 662 kiloelectron volts. But we've now learned that over here, channel 707 is apparently 1,461. Let's double check that against the paper. We now have experimentally confirmed that that's the right channel, 1461. Yeah, that's right, for potassium 40. So that changes things a little bit. Notice the numbers have all changed a little bit, but that's okay. We're now more accurate than we were. So let's leave these regions of interest selected. Clear the spectrum. Let's take the radioactive material and put it away where it can't, affect the spectrum. And we're going to start it up again with the sample. Now I'm going to put the video on so you can see the sample being put into place. All right, now I started out with a can of potassium light salt from the grocery store, but it wasn't building a spectrum fast enough. It would have taken me 2 or 3 hours to get a good clean potassium spectrum from this. I put this on my food though. So I went out and got this big bag of potassium chloride salt that I had. This is water softener salt, the water softener pellets. This stuff is nice and hot. And you buy it at the, you can buy that at any home improvement store too, which is really funny. Okay, so let's put gloves on. Normally I'm involved in what's called non-destructive testing, which is where you put something in and you don't damage it, you just kind of test the object itself. For these noodles, I did a little destructive stuff to them. I kind of broke them up and put them in here because nobody was going to eat them. I mean, they're years old, they're not really suitable for eating at this point. And as a result, I'm not worried about the lead contamination. If I were actually going to test food, which I already said, by the way, I don't necessarily advocate everybody doing, but I've tested my own food before, so there's me being a hypocrite. I would make sure to keep the lead and the food completely double sealed, triple sealed, and away from one another, because you don't really want to get lead in there. Because quite frankly, lead can cause mutations, cancer, and other things just like radiation. I'm not saying that they're absolutely equivalent to one another or exactly equal. I'm just saying they both can. So if you're worried about one, you might as well be worried about the other, right? So we're going to... Wow, I keep dropping the noodles everywhere. Normally I try not to spill stuff. This is a borosilicate testing thing, which I usually actually use, but I can't use it right this second because it won't fit in this, and I don't have the entire lead castle in here. I have almost 200 pounds of lead normally. This is just a little bit of it. So we're going to seal this up for testing purposes. And kind of get the air out of it. I got to squeeze it up against myself to get the air out. Okay. So I used a bottle cap to prop the bottle here up on it. What we're going to do now is we're going to take the beta shield and we're going to stick this in here. Now I spoke with the gentleman who gave this to me a little while ago, actually on the computer on radiationnetwork.com. I was talking to the person, and it was kind of funny. They pointed out, they were asking me about strontium-90, and I should point out that if strontium-90 has any contamination going on in here, if that has anything to do with it, which I doubt, but it's possible, gamma spectroscopy wouldn't show it to us at all. And in fact, the potassium could be low enough that we might in 1 hour not be able to pick it up at all. So we'll see. Like I said, this could be a fail. That's one reason I put the uranium on in the first part. I wanted you to see that it matched the background too, but I also wanted you to see that you can fail and succeed. So we're going to find out. This is a live or die thing. Consider it like drama, like one of those TV shows. All right, so lead is a pain to work with, let me tell you. All right, put that in place. Take the potassium and the cesium and take them out of the room because they will do nothing but confuse us. Let me take them out of the room. All right, good. They're now gone. And I'm going to start this test for 1 hour on time lapse, and let's see what we get. All right, we're fully calibrated, ready to go. Let's go for setting time. Make sure it's set correctly, 3600 seconds. Time is about 5:30, so it will be done at about 6:30, plus or minus. Everything is away from the detector that could cause impurities in what we're seeing. Let's start it. All right. And we are in linear mode, and we'll change that to the lowest setting we can get so we can see. And I'm going to leave the mouse on the potassium ROI so you can see the net counts and the gross counts. Just in case you're curious, what that would be is the gross counts are how many counts were detected right in the middle of this channel. We'll put it right on 1461, so it's right dead in the center. That's how many this, not the whole, that's how many the entire region of interest is picked up, actually. Excuse me, the whole region of interest picked up 5 counts. And based on the rest of the spectrum, it'll calculate how many of them it thinks are plus or minus. Currently, there's not enough data to know that. So anyway, we'll see. I should probably change that a little bit. So there we go. So it's a little bit greater because, it's actually filling up pretty quickly. So I will see you guys back in 1 hour. Alright, so we have now done 1 hour. Let's reduce that a little bit. Alright, we've done 1 hour. First thing that we do, first most important thing we do is save. You would not believe how many spectra I've killed by not saving. No, don't name it that. That's the background. There we go. Okay, now we can see some features in here that look like they're jumping right out at us, but remember that these were in the background as well too. So let's do this the way we should. Step 1. We're going to open up the sample spectrum, the one we just did. Yeah, I know it's in the other screen, but we should open it up separately so we're not messing with the sample we tested. Here it is. We're going to clear out these regions of interest. Now, we're going to, using Notepad, make a note of our calibration so that we can go back to it, because this thing might remove our calibration if we, because we're putting 2 different samples together with 2 different calibrations. Just trust me, this is what I'm doing is particular to the UCS 30 that I'm using right now. We know that at channel 14 we had 32 kV. Where is the other one? Where's the next one? 662, 662, there it is. We know that at channel 344 we had 662 kV, and then over here somewhere we had potassium, which I think, wait, maybe it was here, which I'm pretty sure we have in the sample too, but that's okay. There. So we know that at channel 707 we have 1461 kV. Okay, and you'll see why I recorded that a minute ago. Alright, so what we're going to do is we're going to load the background spectrum. And this is the background spectrum. You see, oh, not load it. I hit the button the wrong way. Load background spectrum, not load spectrum, stupid. Alright, so you see the yellow is the background, the green is the regular spectrum, and they nearly eat over top of one another. See that? Almost identical. Now we're going to strip. This is right here what you're seeing, the remainder of what was left over after I removed them. Not very much, as you can see. Very little came from that sample. You notice that also removed our calibration too. So let's recalibrate quickly. So 3-point calibration in electron volts. It was, oops, 14 was 32. 344 was 662 kiloelectron volts. And what was the last one? 707 was 1461. So channel 707 right over here was 1461. Boing. Okay, so our calibration has been restored. We'll switch to a linear view. Not very much, but there's a little going on here. Let's smooth this. 3-point smooth. Now is when it gets really, really complicated. How do we determine what's what with this? Well, the problem is that most of these areas right here are just little tiny fragments. Let's see if we can figure out some stuff. Let's start by looking at the spectrum we took. Now, when we looked at potassium, we had a region of interest, and let's see where the region of interest was. 1397, so let's create it, 1397, all the way to 1536, about 1536 keV. So boing, there creates the region of interest. Now let's select it with the mouse, and as you can see, it looks to me like this area does, according to this, it has a total of 84 counts, and 83 of them are net, which means that there is something in this area. Let's go back and smooth. It's annoying that it de-smooths it every single time. If we look, there's a little bit of a peak here, not much, but you can see it sort of stands out a little bit, but not too much more than some of these other places do. I would say it's reasonably likely to assume that there might be some potassium in this region here, but there's nothing in this that we can derive without an in-depth statistical analysis, which we're not going to get into this video. Next video I'll get into statistical analyses. Well, not the next video I do, but the next video in this subject, which I will do pretty soon, probably next week. Let's highlight some of these areas and see if anything stands out. Alright, smooth. What stands out to us? I just highlighted the whole area just to make it easier to look at. Alright, well there's a lot going on right here. There's not enough to say there was a peak in this area, but right around 570, 580, somewhere in there. And we've already done some comparisons before, and we see that there's nothing in here that matches that. That would be right over in here someplace. There's nothing really there. There is something on thorium that matches it. The other guys don't match it at all. None of the other spectra that we see here match it even remotely. So the only thing we know that matches it so far is thorium has one that's matching over here. Matches it a little bit, not perfectly. There's a whole bunch going on right in this area too. What is this? 322-ish, 280, 322, somewhere in there. There's 338. So using this method, that still doesn't really match up particularly very well. This spectrum is so weak that we may not be able to derive much of anything out of it. Let's turn on the peak finder and see if it sees anything. Yeah, peak finder sees a little bit, not much though. 325, that's pretty close. 263, that's not very close. 580, not too far off, but nothing at 510. Yeah, let's cut the peak finder off. This spectrum is not particularly hot, but it did see something here where the potassium was. Let's look at that background spectrum again and see if we can compare the two. This is where the investigation comes in. You see how we easily determined the uranium without any problem? We just looked at it and immediately saw it. But when looking at a really trace level contamination sample like this one, it becomes a bit of a pain. Let's compare the background with the actual spectrum itself. Let's compare them in logarithmic view, both of them. So, noodles, no noodles. Noodles, no noodles. And let's smooth this while we're at it so it looks the same. Notice the potassium is there for the noodles. It has the wrong energy because we hadn't calibrated this one right. It's there, but notice it's a little bit broader and less defined. There's always potassium in the background, but in this one it's a little bit stronger, a little more defined. Let's get rid of the ROI so they look the same. And then let's smooth it again. We're looking at the spectrum of the sample. I think the potassium's a little bit more narrow and defined in the sample, which means potassium's a possibility, but when you really look at it, the two are nearly identical to one another. There's a little bit of a change right here in this area, which shows up quite effectively in here, and these are in the 250, 280, 300. This is right where uranium would be. If you recall from our image earlier, this is right where uranium is, in the 200-300 range, meaning we can safely and reasonably deduce that the noodle sample probably has a little bit of uranium in it, which is normal. Most food does have a little bit of uranium in it, tiny little trace amount. Anything else we see? Let's see. I'm kind of switching back and forth here, so I don't want to confuse you too much, but background, noodle, background, noodle, background, noodle. My table just collapsed a little bit under the weight of the lead. Go figure. Not much else. I would say that it is likely that the noodles contain a little bit of uranium and a very trace amount of it, and they also contain a little bit of potassium. I would wager. Without a statistical analysis, I couldn't go any higher than that, and even with one, I probably can't because the activity we're dealing with is so low. But we notice one or two things, if we want to cherry pick some results here a little. let's look at the cesium-137. Let's go look at the broken out one here. Let's see for cesium-137 if we see anything. 662. Right here is where cesium-137 would be. Let me clear this ROI, and let's grab the area around cesium-137. Let's say 640 to 680 kiloelectron volts. And there is a little bit of a peak right here, and it's pretty close, meaning it's possible there could be trace cesium-137 in these noodles. It's possible. But you notice that this area right here that we selected, even though it seems so nice and like a little perfect peak, it's not really any different from a lot of the other ones. Put a grid into it. Do you see what I mean? It doesn't really jump above any of the other ones. Let's see if there's anything at 32 keV. Well, look at that. There's a little bit going on right there at 32. Let's try 28. Oops, let's try 28, 29, 30, 31, 32, 33, 34, 35, 2, let's say 36 keV. And there's a little bit of a peak there, but not much. So even though we do see something right on the dot for cesium-137, it's not very broad like it should be, and overall, I think it's nothing we can really hang our hat on. I will finish this one up, by the way, by doing a longer analysis of it with this better probe and see if I can figure out anything. But for now, I'm going to say the only thing we can say that's in this is uranium-238 and progeny, the decay progeny of it, and maybe a tiny little bit of potassium. And that would be accounting for the beta for sure. As for the cesium-137, it could be in there. That could be there, but I'm going to need to run this many more hours to figure that out. So I'll let you guys know the answer to that later on, because that would be very few becquerels per kilogram for sure. Anyhow, so hopefully this has explained a little bit of it. I'm going to put my little quick handy dandy chart right here that you can use for looking up stuff. I'll put that on the that or a link to it, one or the other in the details. Probably link to it. It might not fit in the details section. And if you go to my website, you can use these images here. I have a lot of them up there, and I'll see if I can put a link to a couple of them. And of course, you may feel free to download these and use them for your own personal studies, but I don't want to see them up on people's websites if you can avoid it, because you know the whole copyright thing and how I don't like my stuff being stolen. Although, just for the record, it gets stolen all the time. What can I do? I mean, I could sue, I guess. So anyway, there you go. This has been Tom from anti-proton.com, and that is not only how you do it, but that's how complex and how complicated it can be when the spectrum is very low activity. So, bye-bye.